Hey everyone, so this is the second part of the wave and nature of light and interference topic. You may have noticed that I skipped a few of those slides dealing with the intensity of the interference waves. You don't really need to worry about it. It kind of briefly goes through the derivation of how you can figure out the intensity of light as it spreads out based off the interference patterns. The only real thing of note from that section is the phasor diagram, which does kind of appear a few more times, not really in this topic, but like in the E&M topic, you might see it for when you start doing AC circuits of LRC type circuits. But for the most part, you don't need to really worry about it too much. So I'm going to continue on talking about the other important aspect of interference, which is thin films. I'm sure everyone's experienced this before. Essentially, you've seen an oil spill on the floor, or you've seen a bubble, like an oil bubble, um, being made or sitting on a plan, I guess. And you may have noticed these rainbow effect colors that you'll see here. So we're actually going to explain a little bit of that right now. Basically, what ends up happening is that light ends up traveling through these thin films, and due to the shape of the thin film, the thickness of the thin film, the way that you're looking at it, what ends up happening is that there ends up being a um, sorry, there ends up being uh, an effect of constructive and destructive interference caused by the fact that light is traveling through that film and interacting with itself as it's being reflected off of the different surfaces. So we're going to be discussing that right now. Basically, what ends up happening is this. So, as I mentioned before, every time a light beam strikes a boundary, there's always going to be a part of that light that ends up being reflected and part of it that gets transmitted. So, here, as it hits the air oil surface, part of that light from section A is going to be reflected back. The other part is going to be refracted and travel through the oil, and when it strikes the water surface, it will then have a section that bounces back again. When it strikes this surface, most of it will end up coming back out, and we end up having these two light beams coming towards you. Now, if these two light beams are in phase by the time they get to your eye, then what we end up seeing is a specific color. We'll end up seeing constructive interference. If they're out of phase, we basically don't see anything. So, in order for us to actually see something, these two waves have to be in phase. But the thing is, one just like with the other interference patterns, this wave has traveled an extra distance that this first reflection didn't travel. So the traveling distance within this oil has to keep this wave in phase. So it's got to end up being an integer wavelength um, path difference in order for the wave as it emerges from this oil section to remain in phase with the first reflection. Now, there's a few other things that we're going to talk about in particular, phase shifts that end up occurring through the reflections, and this goes back to one of the previous sections that I talked about. Uh, in the first section, I think it was the wave section, where I kind of made a comment of, hey, remember this concept about reflection? It'll come back again. So that's now. One thing to kind of remember is the thing that you wanted to remember from before was this idea of hard and soft reflections. So when a wave comes in and it strikes a boundary that has a higher index than it was before, which another way of saying is that it's a slower material, then when it bounces back, it's going to be half phase shifted from before. If, on the other hand, it comes in and the new boundary is um, has a lower index, or it's faster than the original material, then when it bounces back, there's not going to be a phase shift at all. Um, so you want to kind of keep track of that when we're dealing with the light beams bouncing off of these boundaries, is make sure to know which reflections end up being hard reflections, causing this half a wave phase shift, and which ones are soft reflections, ones that result in no phase shift. All right, so a good example is going from air to water is what we would consider a hard reflection. So the light beam that's reflecting off that surface would be half a phase shift, half a wavelength phase shifted. All right, so here's an example. We have two beams traveling. Well, we have a beam coming in, it strikes the first surface, and part of it gets reflected. When the part that goes through the thin film strikes the next surface, that one is also going to bounce back. Now, as we said before, first we're just going to assume that there is no phase shifts at all. Um, well, actually, yeah, so if both of these reflections are, we're first actually just going to assume that they're both hard reflections. The same thing is also going to apply if they're both soft reflections. But we're basically going to say that when it strikes this first surface and when it strikes the second one, there really is no difference between how one's phase shifted from the other. What this ends up telling us is that the thickness of this film has to be such so that the entire distance it travels as it goes from the first boundary to the second and then back has to basically result in a integer wavelength difference. So what we can actually write it as is this. The distance that's traveled, which is 2 times the thickness, has to be equal to m lambda, some integer number of wavelengths, divided by n, or n2. Why is it divided by n2? Mainly because of the fact that as it enters into this new medium, it is now going to be traveling, and its wavelength is now going to be different in that section. So we have to use a form of Snell's law to kind of relate the wavelength and the index of refraction to figure out what the new wavelength in this material is. So this is basically its wavelength in air, if you will. So if instead only one of these reflections was hard and the other one ends up being soft, so one of them gets half a phase shift while the other one gets no phase shift, then this thickness has to be such that we get in a half integer wavelength. So instead of it being m times lambda over n2, we have to add this m plus a half. So um, depending on whether we have a a single hard reflection or a double hard reflection, it's going to change what type of interference we're going to need to be either m or m plus a half. Just like the previous double slit that I talked about, the m in this case actually is going to start at 0, mainly because that's the smallest non-zero number that you could put in for this. That 0 plus a half gets you a half. This is what I was just saying before about why is it lambda over n2, and it's caused by this form of the index of refraction, basically relating index of refraction to the speed of light, or the speed of the light wave, and setting the original wavelength to be the wavelength in air, where n equals 1. Now, so the way you would do this is here you look at this, you have air striking this coating surface. This would first reflection would be a hard reflection, so it would be this first one would be half a phase shift, going from this one to this one, there would be another hard reflection, so half a phase shift. Because they're both half a phase shift, that means it's going to be an integer number. So I'm going to use the m lambda form of the equation. Here, this is only a single hard reflection. You get the hard reflection on the air to soap film reflection, but not on this one. So this one is half a phase shift, while this one is zero phase shift. So that's going to give us, means that we're going to use m plus a half in this case. The thing I recommend is that when you're doing these problems, I kind of recommend that you write on top of the two reflections, whether it's a half phase shift for hard reflection or a zero phase shift for a soft reflection. And then that's going to tell you whether you're going to have a integer value for m or a half integer number. So for example here, when I do, if I were to do that, I would have gone half and a half, which basically equals 1. So that tells me it's going to be an integer wavelength. So I'm going to use the m lambda for constructive interference. Here I would have had half and a 0, so that tells me it's a half integer number. So it's because that's equal to a half. So I'm going to have a half factor thrown in next to that m. So I don't know if that might help. To me, that's what kind of helps me out is to remember. Oh, I don't know if I mentioned this, but if we want constructive interference, we do kind of the same concept that we did for the double slit experiment, where if this gets constructive interference at integer wavelengths, then it's going to get destructive interference at half integer wavelengths. As opposed to this, where if we want constructive interference at half an integer wavelength, then we get destructive interference at integer number wavelengths. So just keep that in mind about whether we're looking for constructive destructive and whether it's a single or a double hard reflection. All right, so you can work on this question, pause the video, we'll go over it in a second. All right, so they want the smallest thickness that the soap bubble can be, and according to this, it's going to end up being a single hard reflection. We're going to get the hard reflection on the first one, but not on the second surface. So that means I'm going to have half plus a 0. I'm going to make this m plus a half here. So when I do that, I plug my numbers in. They want the smallest, so I'm going to make m as small as possible so that I get a non-zero number, and that would be 0. So plugging that in, I get lambda over n times 2. Solve for t for the thickness, plugging my numbers in, and I end up getting that the minimum thickness would have to be 100 nanometers. So if I look at this, 100 nanometers would give me the color green. One thing that I want to note before I move on, you're going to notice that when we're doing this, we're assuming that the light ray is pretty much coming in almost perpendicular to the surface. They're giving it a slight angle just so that we can, visualize the two waves coming out a little bit easier. But we're assuming these cases we're coming in at such a direct angle that it's essentially only going there and back. One thing to note is that if we were to consider that we're looking at these sections that aren't in our direct line side, where maybe the light rays coming in like here, what we're going to end up having to, what we would have had to do is change our equation to take into account the angle that the light is coming in at and bouncing off at. So you may notice that when you're looking at a thin film, like in real life, it's going to go circularly, certain colors, and then as you get further out radially, it changes its colors. We're not going to talk about that, but what's going on is that the reason why you can see different colors, even though the thickness of the film may be consistent throughout the bubble is mainly because of the fact that when the light comes in at angles, it's traveling much different distances than when it's coming straight inward. Hopefully that makes a little bit more sense. Unfortunately, I can't really draw a picture that well. So if you want me to try to explain that a little bit more, ask me later on. But for the most part, we're only assuming that the light's coming in straight on. All right, so here's another question. You can pause the video, work on this yourself, and we'll go over it in a second. All right, so they want to know how thick the film has to be in order for us to see the red light. So once again, we're doing constructive interference. Now we have to figure out whether this is a double or a single hard reflection. It says that it goes from, we're assuming that it's going to go from air. It's going to strike the soap, which has a higher index, so that's going to be a hard reflection. And then the soap is on top of a piece of glass, which makes it another hard reflection. So we end up getting two of them. This is a double, which means that my constructive interference is going to be an integer wavelength. So it's just going to be straight up m. And the smallest number will end up being 1. So plugging my numbers in, setting this for the minimum thickness, and we end up getting 240 nanometers here. All right, here's another question. You can pause the video, work on this yourself, and we'll go over in a second. All right, so they want us to basically figure out they have this fairly complex setup here, and they want to know the thickness of these two materials so that we get the most reflection based off of the wavelength. All right. And basically, they tell us that these indexes keep getting bigger. So that means they're all going to be double reflections, or sorry, hard reflections, because it's going to be, and that's going to mean that we're going to use the integer 1 in that case. So doing this, I'm going to get that the first one has to have a thickness equal to lambda over 2n, n1. And then the second one, pretty much same thing. So easy peasy, nothing really crazy in that case. Again, the whole idea is that this has to be such so that it's ends up coming out at the same phase as the original one. I don't normally have to take into account this thickness for this second reflection, only because this is already keeping it in phase with the original one. I might have had to have taken into account if they were different reflections. If maybe one of the other reflections was a soft reflection, then it might have been a little bit crazier, and I probably would have to take the one of the other thicknesses into account. All right. So you can pause this video, work on this yourself, and we'll go over it in a second. All right. So they want the minimum thickness. So they have two parts. One where we're going to figure out when it appears dark, and then when it's going to appear bright. So basically, they want one destructive interference where they end up being out of phase, and one constructive interference where they're in phase. So they say that there's an air layer between two glass surfaces. So what that's going to tell me is that I end up having a single hard reflection. So I'm going to end up having, let me pull up a picture. I'm going to end up having air over here. I'm going to have glass here. I'm going to have air over here. And then I'm going to have essentially another piece of glass, which really doesn't matter. But what I'm going to end up having is one hard reflection over here as it's entering into the glass, and then one soft reflection over here. So if I want to draw this out, I basically get that this is half, this is 0. So I should be using the half integer form. But that is for constructive interference. For destructive interference, I would then do the integer one. So it kind of takes a little bit of time to kind of get used to it. So I end up getting this. When I plug the numbers in to find the minimum thickness for darkness, it would have to be 340 nanometers. For the brightness, I'm going to take the half integer form, plug the numbers in, and I end up getting the 170 nanometers. Now, one thing I want to note real quickly is that it honestly doesn't matter if you, instead of doing it like this, you actually treated it like it was going from glass to air to glass, because you would have actually had the same thing. So it would have went through glass, part of it would have been reflected. This would have been a soft reflection, so no phase shift. Then the one that goes through here, this would have been the hard reflection, so you still would have gotten the half. So it doesn't change at all there. All right. So that's it. That's all you have to do with the thin film. For the most part, you just have to be careful. If you want, you can make a little table for yourself. So I'll try to whip one up real quick. So it could be something like this. So constructive and destructive. We'll call this single and double. So for the single reflection, oh, like that. For the single reflection, it should be equal to the constructive would be m plus a half, while destructive would be just m. For the double, it would be m for constructive and m plus a half for destructive. So you could feel free to use this to kind of make it a little bit easier. You just ask yourself, is this a single or double? Am I looking for constructive or destructive? And this will tell you whether you're using m plus a half or m. Whatever makes life easier for you. This kind of goes through a lot of the steps that you would do, the same way that I kind of explained it, where you're trying to figure out whether it's going to be constructive or destructive, whether it's you're looking at a full wave difference or a half wave difference, and whether there's any sort of phase shift occurring through the reflections on any of the two surfaces. All right. So there was an experiment done in order for us that we can use to kind of make very high precision measurements. It's called the Michelson interferometer. What this ends up doing is the way it works is we have a light beam coming in, and then we have a mirror which ends up acting as a beam splitter. So part of the beam ends up being reflected towards another mirror, and then the other beam transmits through towards a second mirror. So you end up having two mirrors and a splitter. Once that happens, it strikes this fixed mirror. Both beams will end up bouncing back and transmitting through a person's eye, or through a recording surface. Basically what you end up doing is you can move this mirror a bit until you get these two waves as they come in being completely in phase. What this allows you to do is you can kind of use this to figure out the wavelengths essentially of whatever light source that you're using. by adjusting this movable mirror and seeing what position, how much you can move it in order to see con- uh, adjacent constructive interference. And that would be based off of the wavelength of the light that you're actually sending through this interferometer. Um, yeah, so that's pretty much it. So here it actually says that we can end up measuring one of the mirrors by essentially 100 nanometers. So pretty good measurement for high precision. So yeah, these were the things that we've talked about. Like I said, this is our bulk equation that for the double slit, which is going to come back when we start talking about diffraction patterns. This is for constructive and destructive, the bright bands and the dark bands. We also talked about the thin film interference and how that relates to things like hard and soft reflections, and how we'd figure out thickness from that. All right. The homework is going to be due on on Monday, um, all from chapter 34, and these are the questions. As you can see, both these topics and concepts are equally important. So don't think that one is more important than the other. Um, this one is definitely one that you kind of want to know, though, mainly because we're going to be doing something a lot similar in the next part. Thin film tends to be trickier for people, so try not to ignore that one either. All right. If you have any questions, please let me know. Otherwise, I'll see you later. Bye.